Hi, I'm Shamal, and I'm excited to share our work on revisiting the video in video language understanding. With videos, we have the ability to understand rich language descriptions and questions about event relationships over time. In this video, we see the person bends their knees because they are skiing. But if we were to pause the video and select a single frame, we could probably answer this question without any temporal information. And this raises the question, how well does image-centric understanding address video understanding? This fundamental question has been examined many times before for video-only action recognition with significant impacts on the field. Our focus here is on videos plus language, where language can describe more complex events and event relationships. More broadly, the promise of video language understanding is the ability to go beyond image-centric understanding, from scenes, people, and objects in a single frame, towards temporality, causality, and dynamics across multiple frames. Standard benchmarks can contain a mixture of both, parts solvable with image-centric understanding and parts requiring video-level understanding. In this work, our goal is to analyze this question to get insights for future video language dataset and model design. Now, how do we answer this question from an image-centric perspective? Well, standard approaches process a random frame, or try mean pooling. This is fine for some videos, but many videos can be naturally noisy and challenging. Some frames are clear, but others have motion blur or awkward angles. This means standard approaches may underrepresent an image-centric bound for videos. So let's revisit our core question, but now with a well-selected frame for each video. To do this, we propose the atemporal probe, or ATP, a new image-centric model which learns to perform the selection atemporally or without temporal information. ATP builds on top of a frozen image language model, like CLIP. And specifically, we take the input video and language and sample a sparse, unordered set of frames to encode with our image language model. These representations are frozen and never updated. We then pass them to ATP without temporal information, and ATP learns to make a discrete selection of a single image-level encoding from this set. Importantly, this encoding is passed unmodified to the final video language task. It contains only the information we can get from a single image. And there's no downstream learnable parameters either. Please see our paper for details on ATP's design and training. Now let's analyze standard video language benchmarks with ATP. Here we have two benchmarks on general and instructional videos. Here's the state of the art. And here's the random frame and mean pool baselines. And now here's ATP. ATP improves the image-centric bound significantly with a surprisingly strong performance. For datasets, this suggests large portions can be well addressed with image-centric understanding. And for models, it suggests processing potentially noisy frames might be holding them back. We close the loop on both these takeaways later. We also take a look at NextQA, a recent benchmark explicitly designed for causal and temporal video language understanding. Here, ATP offers a surprisingly close accuracy to the state of the art, and our same takeaways hold. Qualitatively, ATP learns to select relevant frames from noisy ones. For some cases, one frame is enough, but for other cases, ATP selection is still not enough since you need multiple frames. Our paper has more experiments and visuals. Now we close the loop, and we show how ATP can help video language dataset and model design. First, datasets. ATP can identify examples that need multi-frame video-level understanding. Applying this to NextQA, we see ATP better disentangles temporal and causal subsets. And this hard subset better highlights contributions of time and motion design components in video-level models. We think ATP is a promising tool for in-the-loop design going forward. Finally, ATP can plug into video-level models as kind of a pre-processing step to surface meaningful frames to reason over. Our combined approach substantially improves state-of-the-art accuracy and efficiency. In summary, ATP offers a strong image-centric bound and can help improve video language dataset and model design. For more, please visit our poster and project website. Thank you.